3I Atlas didn't just pass by Mars. It illuminated it in a way no natural comet ever should. A faint, structured light detected first by the Mars Express orbiter has reignited the debate about whether 3I Atlas is behaving as a natural visitor or as something far more deliberate. Before we go deeper, like and subscribe so you don't miss the next update. Tell me where you're watching from and what exact time it is right now. I'm mapping the moment you first heard this, across cities and time zones. Here's what we now know. What began as a minor flicker near Mars has turned into a data-driven mystery that may change how we read light itself. It began with a single pixel, a faint rise in luminosity buried deep in a calibration frame that wasn't supposed to contain anything at all. The Mars Express orbiter had been conducting a routine background scan on October 12th, meant to fine-tune its optics for the next imaging sequence. These scans are usually discarded. They're static fields used to balance sensor exposure against cosmic noise. Yet when one of the engineers replayed the feed frame by frame, a subtle pulse appeared along the lower margin of the image, a glow that came and went as if breathing. At first, it was catalogued as a compression error. Spacecraft cameras often misfire under extreme contrast between Mars's surface and the surrounding black. But when the data were cross-checked against a second exposure taken just 12 minutes later, the same flicker appeared not identical in shape, but identical in timing. The anomaly repeated at an interval that no natural artifact should sustain. Every 9.8 hours, the same rise and fall in brightness returned. It was too slow for instrument interference, too stable for cosmic rays, and too deliberate for randomness. The location was even stranger. The source of light wasn't on Mars, nor within the field of any reflected sunlight. Triangulation placed it roughly 730 kilometers behind the visible trail of 3I Atlas, the interstellar traveler that had just passed near the planet days earlier. At that distance, nothing should be bright enough to register on the sensors. Yet the glow persisted through filters, through angle changes, through orbital realignments. Something near the comet's path was emitting its own rhythm of light. Scientists initially suspected solar-wind interaction. Mars has no global magnetic field, so the charged particles around it tend to scatter unpredictably. A sudden plasma surge could, in theory, create brief flashes, but the wavelengths didn't fit. The flicker peaked in the near-infrared range at roughly 3.6 microns, a band normally associated with thermal reflection, not particle impact. Even more unusual, the emission had a constant amplitude. It wasn't fading as the comet moved farther from the planet. When the signal was reprocessed through ESA's photometric smoothing algorithm, the curve flattened into an almost perfect sine wave. Every crest and trough lined up precisely, each separated by the same number of minutes, with no deviation greater than a few hundredths of a percent. Nature can be rhythmic, but not that rhythmic. Even pulsating stars drift slightly in their cycles due to temperature and density shifts. This, however, behaved more like a beacon than a variable light source. In a meeting at Darmstadt, one of the data analysts quietly asked the question nobody wanted to voice. What if it isn't reflecting? What if it's transmitting? The idea was quickly brushed aside. No one wanted to speculate on intentional emission without solid proof. But privately, teams began to dig through past records of 3I Atlas to see if the pattern existed earlier. The answer was unsettling. JWST's infrared camera had captured a similar but weaker modulation 3 weeks before the Mars encounter, so faint that it had been filtered out as background drift. When those older frames were realigned with the new sequence, the phases matched perfectly. Whatever this flicker was, it wasn't local to Mars. It was traveling with 3I Atlas itself, pulsing steadily as the object crossed the inner system. Even small differences in instrument timing can create ghost patterns, but here the synchrony extended across multiple observatories and platforms. European, American, and independent ground telescopes, each confirming the same periodic rise in brightness and the same interval. Statistically, that coherence should be impossible. By the time the data reached public archives, the amplitude had already been downscaled and the anomaly buried in calibration notes. Yet for those who saw the raw feed, the conclusion lingered. It wasn't random noise. It was a flicker that repeated like a clock, precise, patient, and very much alive. The first assumption was simple. One source of light, one explanation. A comet even an interstellar one, should produce its brightness through a single mechanism: reflected sunlight or outgassing from its icy surface. But the readings from 3I Atlas shattered that rule almost immediately. When astronomers overlaid data from ESA's Mars Express and NASA's Deep Space Network, the light curve didn't behave like a single point source. It split. Two distinct peaks, separated by fractions of a second, began appearing in every observation cycle. At first, this looked like a software artifact. Cameras sometimes register a ghost image when strong radiation bounces inside their sensors, especially when pointed toward a high-contrast target near Mars. But the dual peaks weren't random. They were stable, recurring in perfect sequence over 6 consecutive observation windows. One signal remained steady, a calm, unwavering emission with almost no phase shift. The second danced slightly, its intensity modulating with a precision that suggested interference rather than coincidence. Together, they formed what scientists later described as a beat pattern, the kind of signal that appears when two coherent sources interact with each other. When the team at Darmstadt modeled the data in frequency space, they discovered that each emission had its own harmonic signature. The first was broad and diffused, the type expected from a thermal reflection off a dust-coated surface. The second, however, was narrow, laser-like, and astonishingly stable, a spike so sharp it could only be generated by coherent emission. In nature, that kind of stability exists only in phenomena like pulsars or masers, where energy is amplified in magnetic confinement. But 3I Atlas wasn't dense enough to behave like a star. It was a traveler made of rock and volatile ice, hundreds of meters wide, now displaying properties reserved for stellar physics. The dual source seemed to oscillate. As the comet moved farther from Mars, the two emissions shifted in balance, as though exchanging dominance. Sometimes the steady source dimmed while the sharper one brightened. Other times, both synchronized briefly, amplifying the total luminosity by more than 20% before falling back into rhythm. This pattern suggested not just interaction, but coordination. One proposed explanation was magnetic coupling. Mars's weak local magnetic anomalies could, in theory, distort the plasma envelope surrounding 3I Atlas, creating twin zones of excitation. Yet this required the comet's magnetic field to be highly structured, almost engineered. For the dual emissions to stay in phase over thousands of kilometers, the magnetic field lines would need to remain stable and symmetrical, an alignment that defied both turbulence and randomness. The James Webb Space Telescope added another layer of confusion. When it focused on the same coordinates, its infrared sensors detected the emissions at slightly different wavelengths, one peaking at 3.4 microns, the other at 3.7. These differences were too clean to be noise. They represented two distinct thermal states existing simultaneously within the same object. In laboratory conditions, that kind of split signature happens when light passes through two materials of very different composition, layered in close contact, like a shell over a core. If the data were correct, 3I Atlas wasn't just a rock venting gas into the void. It was a composite, an external layer radiating broad thermal energy, and an inner region producing coherent emissions that pulsed with mathematical regularity. When engineers mapped the signal positions across multiple observations, a geometry began to form. The weaker emission trailed slightly behind the comet's visible nucleus, while the stronger pulse led ahead of it by a fixed angular offset of 4.9 degrees, the same angle as the object's original approach, plane into the solar system. It was as though both lights were bound by an invisible axis, rotating together, yet distinct in purpose. By late October, this phenomenon was known among researchers as the dual source problem. It wasn't just about two lights. It was about two behaviors, one passive, one active, working in tandem. In official reports, ESA referred to them as synchronous emission lobes. But internally, some scientists used another word, nodes. If 3I Atlas carried two synchronized emission nodes, one absorbing, one transmitting, it implied organization, structure, and perhaps a function. Nature rarely builds systems that behave this way, but engineering does. Whether it's deliberate or emergent remains unknown. What is certain is that the dual source pattern hasn't vanished. Even now, each time the comet enters solar view, those twin lights flare again, like two halves of a single heartbeat, echoing across the orbit of Mars. Confirmation didn't come from a dramatic event. It came from quiet persistence, a few lines of data inside a calibration log from ESA's Mars Express orbiter. The spacecraft had not been pointed directly at 3I Atlas when the anomaly appeared. It was performing atmospheric limb scans, measuring the thin haze above Mars's surface, when a repeating infrared spike began to contaminate its readings. What should have been a smooth curve of CO, two absorption lines instead showed a tiny rhythmic pulse. Every 9.8 hours, the same modulation resurfaced, the same frequency that had already been noticed by ground-based observatories weeks earlier. At first, Mission Control dismissed it as stray light from the sun reflecting off the spacecraft's solar panels. But a second instrument on board the SpyCam infrared spectrometer recorded the same anomaly from a completely different angle. The signals matched perfectly. There was no hardware interference. The flicker was external, constant, and aligned with the comet's position relative to Mars. To verify it, the team at the European Space Operations Centre synchronized Mars Express with ExoMars Trace Gas Orbiter's telemetry. Both spacecraft scanned overlapping portions of the sky where 3I Atlas had just passed. The result was unmistakable. Each recorded the same pulsing curve, offset by a few milliseconds, exactly what would be expected from two observers separated by a few hundred kilometers, receiving the same external signal. The pattern was now triangulated. It wasn't a glitch. It was real, and it was near Mars. When the datasets were cross-correlated and converted into three-dimensional models, a strange geometry appeared. The intensity of the flicker wasn't uniform. It strengthened when the comet's illuminated hemisphere faced Mars and weakened when it turned away, as though a beam of light was rotating inside its coma. The orbital geometry meant that if the emission were purely reflective, Mars should have acted as a mirror, scattering sunlight at random angles. Instead, the reflections behaved like a directed cone, an organized narrow fan of energy. ESA scientists compared it with natural auroral emissions, since Mars occasionally glows in ultraviolet when its upper atmosphere interacts with solar wind. But the wavelengths didn't fit. The Martian aurora peaks in UV at around 120 nanometers. The 3I Atlas pulse occurred in the near-infrared range between 3.4 and 3.7 microns. That placed it deep in the thermal region, far too low to be a magnetic phenomenon. Something was radiating controlled heat, not ionized light. As the investigation expanded, the mission team began to reconstruct the timeline of events. The first confirmed pulse coincided precisely with the comet's closest approach to Mars. The subsequent pulses remained phase-locked to the same interval, even as 3I Atlas receded from the planet. This constancy suggested that the emission wasn't a reaction to local conditions, it was an intrinsic behavior of the object itself. A kind of internal clock that didn't care about distance or solar influence. To rule out an imaging error, the engineers repeated the process during the next orbit, adjusting exposure times and using different detectors. Again, the same rhythmic light. The amplitude, though small, remained measurable and coherent. The conclusion inside the ESA telemetry summary was cautious but clear. Periodic infrared emission consistent across multiple sensors. Source consistent with Comet 3. I Atlas. 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 When the data reached the public archive 2 weeks later, those lines were quietly omitted. What remained were sanitized plots, smooth, unbroken, ordinary. But by then, word had already spread within the research community. The Mars Express readings had confirmed what earlier instruments could only suggest. The pulse was not local interference. It was a signature. Several independent astronomers in Chile, Spain, and Japan began their own follow-up campaigns, pointing their telescopes toward the coordinates provided by ESA. They too detected the subtle brightness wave moving through the coma. Every crest lined up with the orbital models derived from the Mars Express data. The odds of this synchronization happening by chance were effectively zero. For the first time since its detection, 3I Atlas's anomaly wasn't speculation. It was independently confirmed, observed across instruments, and anchored in numbers that could not be dismissed. In official documentation, the wording remained sterile. Infrared periodicity of uncertain origin. But off record, one scientist from the mission phrased it differently. He said, "We expected reflection. What we got was response." Mars Express had done more than confirm a pattern. It had revealed intent, or at least the illusion of it, encoded in light that beat like a distant pulse, steady, unwavering, and utterly foreign. For a while, it seemed as though the strange structure seen inside 3I Atlas had vanished. After its close encounter with Mars, subsequent telescope frames showed only a soft haze of green light, the familiar glow of diatomic carbon that most comets display when sunlight breaks down their gases. But when the new calibration images from the ExoMars Trace Gas Orbiter were re-examined, something inside that haze shifted. It was faint, symmetrical, and hauntingly familiar. The shell, the same geometric veil that scientists had quietly debated months earlier, had returned. This time, the detection was accidental. The orbiter wasn't searching for the comet. It was studying dust storms above the Martian equator. A background filter meant to correct optical scatter revealed a circular distortion around 3I Atlas's coma. At first glance, it looked like an imaging ring, a common artifact caused by overexposure. But when the data were processed frame by frame, the ring moved independently of the comet's body. It wasn't an error. It was a structure, a green halo that seemed to rotate and breathe. ESA's imaging team applied spectral decomposition to the light curve. What they found was impossible to explain through standard chemistry. The green emission wasn't diffused evenly as it should have been if caused by gas fluorescence. Instead, it was organized into a lattice of alternating high and low intensity, almost like the ribs of a sphere. The spacing between these bright arcs remained constant across multiple observation angles, suggesting physical coherence, as if the coma were wrapped around something that was shaping its glow from within. To confirm this, analysts cross-checked older data from the James Webb Space Telescope. In the near-infrared range, faint traces of the same pattern had been captured weeks before, but too weak to notice then. When enhanced and overlaid on the new ExoMars observations, the alignment was uncanny. Identical angular spacing, identical rotation rate. It was as if the entire shell had resurfaced. More visible now that the comet had moved deeper into sunlight, astrophysicists quickly looked for natural explanations. Cometary shells can sometimes form when jets of gas erupt from beneath the surface in regular intervals, carving ring-like shapes as they rotate. But in those cases, the symmetry breaks down quickly. The shell around 3I Atlas did not. Even after 8 full rotations, the pattern stayed intact, too precise to be the product of random outgassing. When polarization filters were applied, the green light revealed another anomaly. Its polarization axis was offset by nearly 12 degrees from the comet's spin axis. That meant the emission wasn't simply reflecting sunlight. It was being organized, twisted by some internal alignment of particles or fields. In plain terms, the glow wasn't chaotic. It was obeying a hidden geometry. By late November, several observatories on Earth had begun to see the same formation. In Chile, the Las Campanas telescope captured deep-field images, showing concentric ripples extending outward like waves on water. Each ripple pulsed faintly in the same 9.8-hour rhythm that Mars Express had recorded earlier. Somehow, the light and the structure were synchronized, one breathing in color, the other in motion. The implications were unsettling. If the shell was simply gas, it should disperse in hours. If it was dust, it should drift apart under solar radiation pressure. But the shell around 3I Atlas held its shape, rotating like a slow-turning lantern. Its green intensity even fluctuated in harmony with the infrared pulse still measured from its core, as though the two layers were connected inner mechanism and outer display working in tandem. Within ESA, the term structured coma began circulating in quiet internal notes. It was safer than calling it a shell, yet the image spoke for itself. A perfect geometric halo, suspended in a living fog. Some scientists compared it to plasma confinement seen in laboratory magnetic fields. Others noted that the pattern bore resemblance to the diffraction rings produced by coherent light. Light that isn't scattered, but guided. In public releases, none of this appeared. The agency issued a short statement describing localized density gradients in the coma of 3I Atlas, likely due to rotational jets. But behind closed doors, the data told another story of a shell that had re-emerged exactly where it should not, glowing in a hue that nature rarely arranges so perfectly. And so, the green shell returned not as an illusion, but as a message written in light, a reminder that something inside 3I Atlas might still be shaping itself silently, rhythmically, with a precision that defies the randomness of space. When the James Webb Space Telescope turned its mirrors toward the region near Mars in late October, the team wasn't looking for 3I Atlas at all. The target was routine, a calibration field meant to test thermal noise correction across Webb's mid-infrared detectors. But within hours of data transmission, a subtle irregularity emerged in the raw feed. Amid the faint glow of dust and background stars, one object pulsed. It wasn't strong enough to trigger an automatic alert, yet it was distinct enough to make a technician flag it for review. Coordinates confirmed it. The light source was 3I Atlas. At first, the anomaly appeared unremarkable. A brief thermal fluctuation within the 3.4 to 3.8 micron band, consistent with a passing reflection, but when the readings were plotted over time, something strange unfolded. The flux didn't fade, it repeated. Every 9.8 hours, precisely the same increase and decrease in brightness returned. Webb's instruments are some of the most stable ever built, capable of detecting deviations as small as a few parts per million. What they were seeing wasn't noise, it was rhythm. The data scientists isolated the emission from surrounding background sources using differential imaging. When the light curve was stretched into frequency space, it revealed two distinct harmonic layers, one broad, thermal, and expected, the other narrow and sharply defined. This second layer was far too coherent for a natural reflection. In laboratory optics, it resembled the pattern of constructive interference as if two beams of light were crossing in perfect synchronization. The discovery prompted Webb's Operations Center at Goddard to run an emergency reobservation. Normally, telescope schedules are fixed months in advance, but the potential of a repeating infrared anomaly warranted special review. Over the next 72 hours, the telescope conducted 4 short observations spaced evenly around the comet's rotation. The pulse never drifted. It rose and fell with a precision that suggested timing, not chance. Then came an even deeper puzzle. As 3I Atlas rotated, the pulse should have shifted relative to its surface, like sunlight moving across a turning object. It didn't. The modulation remained locked in phase, as if anchored to an internal axis, independent of rotation. That behavior had never been observed in any natural body. Even artificial satellites drifting in deep space show subtle variations due to spin and changing light angles. 3I Atlas did not. It was behaving like a source that controlled its own output. Webb's spectroscopic instruments soon added more context. The emission peak corresponded to a temperature of roughly 350 Kelvin, far too high for a body at its distance from the sun, yet too low for vaporized metal. The surface showed no evidence of sudden heating, no flares, no reflective spikes. It was as if the energy were being generated and released internally, through a mechanism invisible to any known process of sublimation or thermal cycling. One engineer quietly suggested an unsettling comparison. It's behaving like a modulator. In radio terms, that would mean the comet's light wasn't random emission, but a carrier wave, a steady base signal upon which information could, in theory, be imprinted. No such claim was made officially, but internally, the observation summary replaced the word flare with pulse. Meanwhile, the ESA and NASA coordination teams exchanged encrypted reports to ensure cross-validation. Goldstone radar data from the same time frame showed a faint echo consistent with the 9.8-hour cycle. Though too weak to analyze fully, it hinted that the optical and radio domains might be linked to two manifestations of the same underlying rhythm. When the time came to release the public data, the pulse was absent from the summary plots. Only a single line remained: transient infrared variation, likely associated with outgassing. But the full resolution frames, preserved in the internal repository, told another story. The brightness curve rose and fell with almost mathematical elegance. Sharp, symmetrical, deliberate. Behind the scenes, the observation became known as Webb's silence. Not because the telescope had failed to capture sound, but because the agency had chosen not to speak. For those who saw the unfiltered data, the conclusion was unavoidable. 3I Atlas was emitting energy too structured to be random. Whether it was natural resonance or something more sophisticated, no one could say. But in the stillness of those infrared waves measured across millions of kilometers, the universe seemed to whisper in numbers, a signal without voice, a light that refused to fade, and a silence that spoke louder than any transmission ever could. Every comet rotates. That is one of the simplest truths in orbital mechanics. Ice and rock, once captured by sunlight, spin their outgassing jets, acting like small thrusters, tilting their axes, creating the flicker and shimmer astronomers have documented for centuries. But when 3I Atlas entered the inner solar system, something about its rhythm didn't add up. The pulse recorded by the Mars Express orbiter, the James Webb Space Telescope, and multiple ground arrays all followed a 9.8-hour cycle. Yet when its physical rotation was modelled through light curve analysis, the numbers refused to match. By tracking the variations in brightness across consecutive frames, astronomers calculated a rotation period of roughly 4 hours. That would be typical for a comet of its size. Slow, stable, steady. But the pulse did not follow that period. The brightening didn't occur when the same regions of the nucleus faced the sun. It occurred on its own clock, drifting further out of sync with each observation. The emission and the rotation seemed to belong to two different systems. At first, this mismatch was chalked up to data latency. Perhaps instruments from different agencies weren't perfectly synchronized. But even after ESA's telemetry team corrected for time drift and standardized all timestamps, the pattern persisted. The rotation of the nucleus and the periodic pulse were not coupled. The object's body was turning at one rhythm, but the energy it emitted beat to another. To visualize this, researchers at the European Southern Observatory constructed a 3D phase map, a rotating model showing how the pulses should align with the comet's spin. Instead of forming stationary hotspots, the pulses appeared to slide across the surface like searchlights moving independently of any fixed point. It was as if the source of the energy wasn't on the surface at all, but hovering inside or around it, projecting outward through the surrounding coma. In natural terms, this is nearly impossible. Jets of vapor and dust always originate from discrete vents or fractures. They rotate with the nucleus, producing predictable flickers as they turn into sunlight. 3I Atlas, however, behaved like a gyroscope inside a sphere. Two rotational systems, one mechanical and one energetic, loosely coupled but not synchronized. One team proposed a magnetic explanation. If the comet carried a residual magnetic field, perhaps fossilized from its birth environment, it might interact with the solar wind in ways that created standing waves of charged particles. These could oscillate independently of the comet's spin, producing a regular external glow. But the field strength required for such stability would exceed anything known. In a body of its composition, the magnetic hypothesis was quietly dropped. Next came the precession model. Maybe the nucleus wasn't rotating smoothly but wobbling, causing apparent mismatches in timing. Yet this idea also collapsed under simulation. The degree of wobble required to explain the phase offset would have visibly distorted the comet's coma. The coma, however, remained geometrically perfect, calm, symmetrical, centered. In November, a paper circulated internally within ESA's science division titled Rotational Decoupling in 3I Atlas. It presented the data bluntly. The luminous pulse is non-rotational in reference to nucleus spin. The signal persists, irrespective of body orientation. In simpler terms, 3I Atlas emitted light as though it were stabilized, not tumbling, not responding to torque, not behaving like anything subject to Newtonian motion. Some scientists compared it to spacecraft attitude control, the ability of a probe to maintain an internal axis using gyroscopic stabilization, or electromagnetic balancing. The analogy was uncomfortable but mathematically valid. The phase difference between the spin and the pulse was consistent with a system maintaining independent rotational control. During one particularly sensitive observation from Goldstone radar, subtle Doppler shifts hinted that the outer coma was rotating in one direction, while the internal emission pattern drifted slightly the other way. That tiny opposition, a rotational mismatch within the same object, became the defining signature of 3I Atlas. It wasn't merely spinning, it was counterspinning. The discovery reignited debates about Oumuamua, the first interstellar visitor ever recorded. That object, too, had shown strange acceleration, inconsistent with its spin. 3I Atlas took the anomaly further, demonstrating not just an external thrust but internal dissonance. The public never saw these plots. The official statement reduced the event to rotational irregularity, likely caused by differential sublimation. But within research circles, another term quietly emerged: stabilized emitter. It described a body whose energy release pattern remained steady, even when its physical form did not a hallmark of control, not chaos. In the silence of space, that control spoke volumes. 2 rotations, 2 clocks, one belonging to a drifting piece of interstellar debris, the other to something hidden within it, dictating its own timing, as though listening to a rhythm no one else could hear. As 3I Atlas curved toward Perihelion, its closest pass to the Sun, scientists expected the same thing they had seen 100 times before. Heat rises, ice sublimates, jets erupt, and the comet brightens dramatically as it sheds its outer layers. That's the choreography of every visitor to the inner solar system. But this time, something different happened. The closer 3I Atlas came to the Sun, the quieter it became. Instead of flaring into brilliance, the object's visible brightness stabilized. Even as solar radiation increased by nearly 40%, its spectral temperature plateaued, hovering at a steady 350 Kelvin. The coma, instead of expanding, compressed slightly. For a moment, it looked as if the comet were absorbing sunlight instead of reflecting it. But when the data from James Webb and the ESA's solar orbiter were compared, a second hidden signal appeared, a faint but regular surge of thermal energy, pulsing outward every 9.8 hours. This pulse wasn't random. It matched perfectly with the rhythmic light variations recorded earlier near Mars. Only now, the phenomenon was happening in the heat domain, rather than the visible spectrum. Webb's MIRI instrument, sensitive to mid-infrared radiation, captured a strange waveform, energy building, gradually, then releasing in a sharp spike before fading again. Each cycle lasted nearly 10 hours, smooth, mechanical, and unnaturally precise. On paper, it looked like a thermal echo, as if the comet were responding to the Sun's radiation with a delayed reaction, absorbing energy and re-emitting it in timed bursts. But natural comets don't do that. Their thermal signatures rise and fall chaotically, as volatile materials evaporate at different depths. 3I Atlas's echo, however, was structured. The amplitude, duration, and frequency of each pulse remained identical, cycle after cycle. The anomaly deepened when scientists tracked the phase relationship between the light pulse and the thermal one. The heat didn't crest when the comet's visible brightness did. It lagged behind by about 14 minutes, like a system processing input before responding. To engineers, it resembled feedback delay, a hallmark of controlled modulation, not chaotic thermodynamics. The team at the European Space Operations Centre ran thermal simulations using every model available: silicate dust, carbon-rich ice, even exotic compounds like nickel carbonyl that had previously been detected in the comet's vapor. None of them could produce the same pattern. To maintain that precise temperature oscillation at perihelion distance would require an active mechanism regulating heat flow, something that could absorb and re-radiate energy on command. At this stage, a few scientists began comparing the readings to known artificial signatures. Spacecraft, for instance, often show thermal echoes when they rotate or adjust power systems near the sunday. The pulses they emit correspond to radiator cycles or shielding maneuvers, but 3I Atlas was hundreds of meters wide, far too large to behave like a spacecraft, and yet too refined in rhythm to be an inert rock. Goldstone radar joined the observation campaign and detected a subtle pattern in the comet's radar albedo. Every time the thermal pulse peaked, the radar cross-section momentarily dropped, as if the outer surface were changing, phase becoming smoother or more reflective for just a few minutes. That kind of synchronized behavior suggested some internal process reorganizing the material, almost like a living system balancing its temperature. By December, as 3I Atlas rounded its perihelion and began its slow outbound climb, the heat wave continued undiminished, stable, and now independent of solar proximity. The comet was cooling in distance but not in energy. The 9.8-hour thermal echo persisted with eerie constancy, as though the Sun had awakened something that now operated on its own clock. In public reports, ESA labelled the readings as anomalous thermal harmonics, but in closed briefings, the language was different. One researcher called it reactive equilibrium. Another used the phrase controlled decay. The implication was simple: the object wasn't just responding to sunlight, it was managing it. For the first time, astronomers began to speak of 3I Atlas, not merely as a traveler from another star system, but as a mechanism, a structure capable of storing, redistributing, and releasing energy with mathematical precision. In the deep vacuum around Perihelion, where chaos usually reigns, 3i Atlas behaved like an instrument, obeying a silent command, a heartbeat of heat repeating faithfully, long after the touch of the sun had passed. When the first spectral holes were discovered months earlier, they were easy to dismiss. A missing wavelength here, a calibration gap there, ordinary noise that could be blamed on instrumentation or cosmic dust. But after the Perihelion passage, as 3i Atlas began to recede from the sun, the holes came back deeper, cleaner, and far too organized to ignore. It started when ESA's ExoMars Trace Gas Orbiter performed its post-perihelion scans, mapping the comet's chemical composition as it moved beyond Mars's orbit. The spectrometers expected the usual clutter: broad emission bands of water, carbon dioxide, methane, and cyanide, the fingerprint of a normal comet. Instead, entire regions of the spectrum were missing. Not weak, not noisy gone, between 3.2 and 3.5 microns, there was nothing. Another void appeared near 7 microns. And most disturbing of all, a sharp black gap stretched between 905 and 950 nanometers, right where carbon-rich dust should have been glowing at its brightest. These missing regions weren't random. They formed evenly spaced intervals, symmetrical across the light curve like the silent bars of an unplayed note. At first, scientists considered detector error. Instruments can sometimes produce flat lines when they're overexposed. But the same gaps appeared across multiple instruments: ExoMars, Mars Express, and Webb's NearSpec, each built by different teams, using different sensors, observing at different times. The probability of all three failing in the same way was virtually zero. When the spectral data were reconstructed into a 3D model, something astonishing appeared. The missing wavelengths formed radial zones across the comet's coma, evenly spaced bands where no photons were detected. Between those bands, the light returned in perfect rhythm. The geometry looked less like a natural gas plume, and more like a pattern, a repeating interference structure that absorbed specific wavelengths and released others in harmonic sequence. The effect resembled what physicists call destructive interference, the same principle used in stealth coatings on Earth, where certain materials are layered to cancel out radar waves. But no natural comet should behave like that. Its gases are chaotic and diffuse, not precision-tuned absorbers. The phenomenon became known within ESA as the return of the spectral holes. Teams compared them to the earlier readings taken before Perihelion. Those first gaps had been shallow, faint valleys across the light spectrum. The new ones were deeper by almost 40%, sharper at the edges, and perfectly aligned with the earlier pattern. The object hadn't lost its anomalies, it had amplified them. Even more intriguing was the timing. The appearance of the spectral holes coincided exactly with the 9.8-hour pulse already documented in both thermal and visible wavelengths. Each time the pulse reached its peak brightness, the holes expanded slightly, as if something inside 3i Atlas was adjusting the way its outer layers interacted with light. In a meeting at Darmstadt, one analyst described the data as structured silence. Where there should have been spectral noise, there was precision. Some theorized that the voids could be caused by layers of vapor arranged in crystalline sheets, thin films of ice, alternating with heavier metal-rich dust, filtering out specific wavelengths through refraction. But this theory collapsed when polarization data showed that the absorption was phase-locked, not diffused. The light wasn't scattering, it was being cancelled. NASA's Goddard Center confirmed the finding independently. Using residual data from Webb's earlier scans, they traced the missing bands to frequencies where molecular vibration modes should occur. Something either material or engineered was suppressing those vibrations entirely, erasing them from the spectral record. In their private correspondence, one researcher called it the optical equivalent of a heartbeat skipping a beat. That metaphor stuck. To the scientific community, the phenomenon hinted at regulation, an entity moderating how it interacted with energy, choosing which frequencies to reveal and which to swallow. When the public summary was finally released, it downplayed the event, describing localized optical attenuation consistent with unknown mineral grains. But the internal reports were blunt. The same harmonics seen before Mars had reappeared, more precise than ever. like a code repeating itself after each solar pass. The idea that 3I Atlas could be actively shaping its own spectrum sounded impossible, yet the numbers left no alternative. Each hole was equidistant, phase-stable, and synchronized with the comet's thermal cycle. Whether it was resonance, reflection, or regulation, the result was the same. The object was controlling its light. In the vast emptiness beyond Mars, 3I Atlas no longer shone as a comet should. It shimmered in patterns, parts of its spectrum erased by design, as if concealing its true composition behind mathematical silence. The spectral holes had returned, and this time they formed a message not in words, but in the deliberate absence of light. The mystery of 3I Atlas deepened when Mars itself began to react. Not visibly, there were no auroras, no storms, no brilliant plumes in the sky, but magnetically. In the weeks following the comet's perihelion passage, as it drifted outward past the orbit of Mars, instruments aboard several orbiters detected subtle, rhythmic distortions in the planet's localized magnetic fields. At first, these fluctuations seemed random, but once the datasets were aligned with the comet's position, a chilling symmetry emerged. Every 9.8 hours, Mars's magnetometers pulsed in perfect sync with 3I Atlas's light curve. The phenomenon was first noticed by the MAVEN orbiter, NASA's mission dedicated to studying Mars's atmosphere. MAVEN's magnetometer recorded faint magnetic undulations, oscillations too weak to trigger alarms but too structured to dismiss. They weren't typical solar wind fluctuations, which arrive in chaotic bursts depending on solar activity. Instead, they followed a clean, harmonic pattern, repeating at intervals identical to the comet's optical pulse. When ESA's ExoMars and Mars Express probes cross-checked their own data, the match was undeniable. Something in the direction of 3I Atlas was modulating Mars's magnetic environment gently, precisely, and consistently. At first, scientists suspected interference from the Sunday solar storms can induce currents in planetary magnetospheres, even weak ones like Mars's. But solar activity during the observation window had been remarkably calm. The Sun's own magnetic field, monitored by the solar orbiter, showed no oscillations at that frequency. Whatever was creating the pulse wasn't coming from the Sunday, it was coming from 3I Atlas. To visualize the anomaly, researchers plotted the magnetic vectors over time. The graphs revealed a recurring pattern, a subtle alignment of field lines bending toward the comet's trajectory, like iron filings drawn to an invisible magnet. The strength of the distortion was minimal, measured in nanoteslas, yet it propagated across the entire night side of Mars's upper atmosphere. More curious still, the oscillations intensified whenever 3I Atlas's infrared pulse peaked, implying that heat, light, and magnetism were somehow linked. In natural physics, that kind of correlation doesn't happen. Light and magnetism can interact through charged plasma, but only in dense environments like stars or magnetospheres. The space between Mars and the comet was too sparse for such coupling. That left researchers with an uncomfortable conclusion. The source of the magnetic modulation was internal to 3I Atlas. A report quietly circulated within ESA under the title Electromagnetic Correlation with Interstellar Object 3I Atlas. It proposed a radical hypothesis. The comet's interior might contain a conducting structure, metallic or plasma-based, capable of generating periodic magnetic fields as it rotated. These emissions, weak but coherent, could travel millions of kilometers through space, subtly disturbing Mars's residual magnetic crust. Essentially, 3I Atlas might be operating like a dynamo. James Webb's mid-infrared observations supported this idea indirectly. During each thermal pulse, the telescope recorded a microshift in spectral polarization, a telltale signature of magnetically aligned dust. It suggested that particles within the comet's coma were momentarily reorienting in response to an organized magnetic field, aligning, then relaxing, like compass needles responding to a hidden signal. Ground-based observatories added another strange layer. The Chilean radio array ALMA detected brief polarization, flips in microwave frequencies during the same windows as MAVEN's magnetic oscillations. Those flips were consistent with an external electromagnetic driver, not a reflection or echo, but an active field sweeping across Mars's orbital plane. Publicly, both ESA and NASA avoided the term magnetic influence. Their joint statement called it transient electromagnetic coupling, likely driven by charge-dust interactions. Yet the internal memos use stronger words. One scientist referred to it as induced alignment, another as directed magnetization. In one particularly telling sequence, the magnetic field around Mars appeared to bend backward, not toward the comet's past position, but along its future trajectory, as though anticipating motion before it occurred. That behavior defied both physics and probability. The field wasn't being dragged, it was being guided. By December, the pulse had weakened, but traces remained detectable in MAVEN's deep archives. A standing oscillation, quiet, faint, but persistent, still echoed every 9.8 hours, long after the comet had left Mars's immediate vicinity. To the public, the event was another footnote in the saga of a strange interstellar visitor, but for the scientists watching the magnetometers twitch in rhythm with a silent pulse far away, the conclusion was far more unsettling. 3. Atlas hadn't just illuminated the space around Mars, it had reached out and written invisible lines across its magnetic field, like a hand brushing softly over the planet's skin. It began, as many moments in science do, with silence. After months of steady data releases, light curves, spectral logs, thermal maps, the European Space Agency abruptly stopped publishing new information about 3I Atlas. No press statements, no calibration updates, not even a courtesy note to confirm that observations were continuing. For most of the public, it went unnoticed. For the small community of researchers tracking the object since its Martian flyby, it was deafening. The lockdown happened quietly on December 12th, 3 days after ESA's Mars Express transmitted its final confirmed dataset showing synchronized magnetic anomalies. The file appeared briefly in the public repository, tagged pending calibration, then vanished within hours. When researchers attempted to access the URL again, it returned a simple message: restricted archive node. Even within the agency, access permissions were suddenly altered. Instruments that had always fed open data streams were now routed to encrypted servers, accessible only to a handful of principal investigators. This was highly unusual. ESA has long prided itself on transparency, from Rosetta's Comet mission to the Mars Express operations. Nearly all raw telemetry is published automatically after preliminary checks. Nothing like this had happened before. The change was not announced. It was buried in a maintenance note citing temporary security compliance restructuring. But investigators noticed something else buried in the metadata. A new classification tag, Tier 4 access required. Tier 4 status is reserved for material deemed sensitive to international coordination. It's typically applied only to data involving military satellites or geopolitical incidents, not astronomy. So why was it now attached to a comet? Behind the scenes, communications between ESA, NASA, and China's CNSA intensified. Meeting logs revealed a flurry of encrypted correspondence over a 72-hour window. One internal summary, later leaked to journalists, referred to anomalous coupling and synchronization anomalies between observation platforms. In simpler terms, multiple spacecraft had begun experiencing minor telemetry lags whenever 3I Atlas was in frame. The delays were small milliseconds but synchronized across 3 independent missions. To engineers, that suggested interference. Rather than admit to interference, ESA classified it. On December 15th, all missions referencing 3I Atlas were instructed to reroute their uplinks through secure relay channels normally used for deep space defense assets. The directive's language was bureaucratic but chillingly clear. Maintain data continuity under restricted visibility. Dissemination suspended until cross-agency protocol review complete. Researchers within the agency pushed back. Many had built careers on the promise of open data. One scientist from the Darmstadt Control Center described the mood bluntly. It felt like the curtain coming down. The data servers that had streamed near real-time information for years now showed only blank dashboards. When journalists asked ESA's press office for clarification, the agency issued a single, sterile statement. Following internal technical review, select datasets relating to interplanetary object 3I Atlas have been temporarily withheld to ensure accuracy before publication. But accuracy wasn't the issue, synchronization was. The instruments were functioning perfectly. What worried Mission Control was that they were functioning too perfectly, producing readings that mirrored one another across vast distances, locked to the same inexplicable rhythm coming from the comet. Privately, some staff referred to the freeze as the blackout. In Darmstadt, telemetry operators noticed that all new 3I Atlas data packets were routed to an internal server cluster labeled Hermes, a codename usually associated with cross-agency relay testing. Access required physical authorization. Overnight, the object that had captivated the world became an internal matter, a digital ghost fenced off behind encryption walls. By early January, external observatories noticed the absence. Amateur astronomers could still photograph 3I Atlas, but without ESA's precision tracking, trajectories became guesswork. A growing number of independent researchers accused the agency of data suppression. ESA responded only once more, repeating that final calibration is ongoing. No timeline was given. Inside the European Space Operations Centre, the last unredacted memo, circulated with a single line at the bottom, a line later quoted in countless leaked summaries. Observation status: persistent anomaly. Review cycle extended indefinitely. That was it. No closure, no press conference, no data. The silence that followed wasn't just administrative, it was procedural containment. 3. Atlas had moved from the realm of public science into something else entirely. And so, ESA's quiet data lockdown became a story not of discovery, but of disappearance. A signal so precise it forced the world's most open space agency to go dark. In the study of comets, dust is the simplest thing to understand. It moves away from the sun always. Radiation pressure pushes the finest grains outward, shaping the familiar tail that stretches across the darkness like a painter's stroke. The direction of that tail is predictable to within fractions of a degree. But when 3I Atlas neared Mars and the high-resolution cameras of ExoMars and Mars Express began their joint imaging campaign, the dust betrayed that rule. Instead of trailing behind, some of it was flowing toward the comet's nucleus, drifting against the direction of solar radiation, as if gravity had reversed or time itself was folding inward. The first indication came from a sequence of calibration frames captured on October 29th. Analysts in Darmstadt were adjusting the contrast of the images when one technician noticed something off about the motion vectors. In the sequence, fine green filaments of dust could be seen curling back toward the core instead of streaming outward. The effect was faint, a slow, deliberate inward drift that appeared almost liquid. Thinking it was a data processing artifact, the team ran the same frames through a different pipeline. The result didn't change. The motion was real. To verify it, ESA cross-referenced data with NASA's Mars Reconnaissance Orbiter. Its optical payload confirmed that faint particulate backflow was indeed visible in reflected light. Even stranger, the effect was phase-locked with the 9.8-hour pulse that had already been detected in thermal and magnetic data. Every time the pulse reached its trough, the moment the infrared brightness dimmed, the dust reversed direction, flowing inward, as though drawn by a hidden force. Then, when the pulse brightened again, the dust resumed its normal outward drift. Physicists immediately ruled out gravity. The nucleus of 3I Atlas was far too small to pull back particles, already accelerated by solar pressure. Nor could electrostatic forces explain it. Those usually cause short, erratic bursts, not smooth waves. Yet the inward drift occurred like clockwork, repeating with each luminous cycle, stable, harmonic, and global across the entire coma. One speculative explanation proposed that the comet's coma contained a plasma sheath, a thin layer of ionized gas surrounding a neutral core. If the object emitted periodic electromagnetic pulses, which it did, according to the magnetometer data from MAVEN, then charged dust could be drawn inward along field lines before being repelled again. In effect, 3I Atlas would be breathing through electromagnetism. But even this model required a degree of stability never seen in a natural body. When the Goldstone radar array was tasked with observing the comet during one of these reversals, its reflectivity maps revealed something even more unsettling. The region of inward motion formed a symmetrical cone, extending precisely along the object's rotational axis. As if a field or structure were guiding the particles with mechanical precision, the cone's boundaries were sharp, not diffuse. Natural jets from comets are chaotic. They spew dust in turbulent spirals. This one was perfect, narrow, and still. By November, the phenomenon became known informally as the backward tail. Amateur astronomers attempting long-exposure imaging of 3I Atlas began to report an eerie split structure, one tail stretching normally away from the Sun, another faint but distinct countertail pointing inward toward the nucleus. It defied every textbook image of a comet. The ESA team tried modeling the event as a simple reflection sunlight bouncing off pre-existing dust lanes to create an illusion of reversal, but this theory collapsed when spectrographic analysis revealed a clear Doppler shift. The particles weren't static illusions, they were genuinely moving against the radiation flow at measurable speeds of 20 to 30 meters per second. Then came the most baffling finding. During the moments of inward flow, the infrared signature of the comet dimmed slightly, as if the incoming particles were being absorbed, not scattered. Some hypothesized that the dust carried charge, feeding energy into the nucleus. In other words, 3I Atlas might have been harvesting its own expelled material, reclaiming it in timed intervals like a closed-loop system. Maintaining equilibrium, ESA's official line described it as temporary phase inversions caused by complex plasma dynamics, but inside the agency, a different term circulated material recall. It sounded mechanical because it was. The dust wasn't simply reacting to sunlight. It was obeying a command, one that pulsed from within. When the comet eventually drifted farther from the Sun, the inward motion faded, the two tails merged, and the object resumed the ordinary behavior of an outbound traveler. Yet, the data remained. The vectors still pointed the wrong way, the timing still matched the pulse, and the mystery still stood. Something inside 3I Atlas could override the most basic force governing a comet's life. The dust had moved backward, and in doing so, it left a mark on every scientist who saw it. Because in a universe built on outward motion, only one kind of thing calls matter home again. Something that remembers. Polarization is one of astronomy's quietest measurements. It doesn't dazzle like brightness or color, but it reveals structure, the direction in which light waves oscillate as they travel through space. For ordinary comets, polarization is simple. Sunlight hits dust, scatters chaotically, and the resulting glow carries a random orientation. Yet with 3I Atlas, nothing behaved randomly. In late November, when ESA recalibrated its optical sensors during a stable phase of observation, the comet's reflected light began showing a pulse of polarization that repeated every 11 minutes, superimposed on its much larger 9.8-hour cycle. The pattern wasn't just visible, it was perfect, sharp, and synchronized across multiple instruments separated by millions of kilometers. It began with the trace gas orbiter's onboard polarimeter, which was meant to map ice crystal orientation above the Martian atmosphere. During background scans, the device caught a faint oscillation in the polarization angle of 3I Atlas's light. The swing was subtle, just a few degrees of shift, but it occurred rhythmically, every 660 seconds. At first, engineers thought it was the instrument's gyroscope recalibrating, but when Mars Express and the Very Large Telescope in Chile registered the same 11-minute oscillation, the explanation collapsed. Polarized light can be produced by aligned dust grains under magnetic influence. The problem was that these grains shouldn't align that fast. The process normally takes hours or days, depending on local conditions. Here, it was happening with clockwork precision, as if some unseen mechanism was flipping the alignment of the coma's particles back and forth on a timer. ESA's polarization specialists fed the data into modeling software, testing every known variable: dust composition, density, and solar incidence angle. None of it reproduced the pattern. The oscillations were too coherent, the shifts too symmetrical. Eventually, they discovered something even stranger each time the polarization rotated. The total brightness of the comet dipped by a fraction of a percent, then rebounded. The timing between light intensity and polarization shift was exact: 11 minutes, 0 drift. This consistency led to one inevitable hypothesis. The light wasn't just scattering off dust, it was being modulated. In laboratory optics, that kind of precision requires interference. Two sources of light intersecting at controlled angles to manipulate wave orientation. It's how humans polarize lasers or encode data in optical transmissions. But in deep space, no known natural process can sustain that regularity. The James Webb Space Telescope added a crucial piece to the puzzle. During a mid-infrared observation session, its sensors detected micro-variations in polarization that matched the visible readings from Mars' orbit. In other words, 3i Atlas was modulating its light across multiple wavelengths simultaneously visible and infrared, both flipping in tandem every 11 minutes. The probability of a random alignment across spectra was infinitesimal. When these results reached the European Space Operations Centre, analysts realized that the 11-minute cycle was nested within the larger 9.8-hour pulse, a harmonic resonance, like a subbeat in a piece of music. Each full 9.8-hour cycle contained precisely 53 11-minute subcycles. The ratio was so exact that engineers double-checked their clocks against the spacecraft telemetry to rule out drift. The numbers held. The object was not only emitting periodic energy, but doing so in layered rhythms like signals within signals. For a brief moment, speculation turned daring. Could 3i Atlas be producing polarized emissions as a byproduct of an internal magnetic process, something rotating rapidly inside its core, inducing an electromagnetic field strong enough to reorient dust grains rhythmically? The theory bordered on science fiction, yet it fit the data better than anything else. If such a field existed, it would imply conductivity and structured rotation features more at home in a reactor than a comet. ESA's official release, when it came, stripped away all of that. The agency described the discovery as localized polarization anomalies, possibly caused by charged dust interactions. But within the internal network, the engineers called it something else. The strobe. The strobe's precision unnerved even veteran scientists. Each oscillation was identical, no drift, no decay persisting for days. It was as if 3i Atlas had an internal oscillator, a mechanism capable of maintaining phase-locked cycles through chaos, dust, and vacuum. When plotted over time, the 11-minute pulses formed a perfect wave, fractal in harmony with the longer 9.8-hour envelope. And hidden within that pattern lay a chilling implication. Whatever was producing these oscillations wasn't losing energy. It was maintaining order, resisting entropy in an environment where nothing should. In cosmic terms, that's not reflection, that's behavior. And in the black silence beyond Mars, for 11 perfect minutes at a time, the light of 3i Atlas moved not like a comet, but like a message repeating itself, steady, deliberate, and impossible to mistake for chance. Nickel is one of astronomy's most dependable markers. It's the fingerprint of a comet's core composition, a metal that forms in supernovae and lingers in dust long after its parent star dies. Wherever we find nickel, we usually find iron too. The two elements are born together, bonded through the same nuclear processes. So, when 3i Atlas was first scanned and revealed nickel without iron, the discovery made no sense. Scientists spent months trying to explain the missing half of that cosmic pair. Some said it was a measurement glitch. Others blamed dust contamination. But as the comet moved past Mars and its infrared spectrum became clearer, a new wave of analysis came in, and the impossible signature returned, stronger than before. The first confirmation came from the James Webb Space Telescope's NIRSPEC instrument. During a long exposure sequence meant to map volatile gases, Webb detected a sharp absorption feature at 7.47 microns, the exact frequency of neutral nickel atoms. It wasn't faint or ambiguous. It was dominant, saturating several frames. But right next to it, where iron should have produced its own spectral line at 7.45, there was nothing. The signal dropped to zero. Once again, 3i Atlas was showing pure nickel emission, isolated, unaccompanied, and inexplicably stable. That spectral purity is unnatural. In ordinary comets, nickel is bound in mineral grains with iron and sulfur. When sunlight heats the nucleus, both metals vaporize together, creating overlapping peaks in the emission spectrum. Yet here, nickel appeared unbound, as if refined. In laboratory terms, the signal matched that of metallic nickel powder, not the mixed compounds typical of space dust. The ratio of nickel to iron in 3i Atlas was calculated at over 400 to 1, a concentration higher than anything ever found in a natural object. ESA's spectroscopy division in Darmstadt tried to replicate the readings using archived calibration standards. They couldn't, even when they simulated possible instrument drift, cosmic ray interference, and detector noise. The ratio remained constant. Webb's detectors weren't lying. 3i Atlas was emitting light consistent with high-purity nickel, That detail alone would have been shocking, but the pattern behind it was worse. The nickel emission wasn't constant. It pulsed in sync with the object's now familiar 9.8-hour cycle. Each time the brightness curve peaked, the nickel signal spiked, as if the material itself were being energized rhythmically from within. In nature, metal atoms don't pulse. They radiate when heated or ionized. Something inside 3I Atlas seemed to be stimulating those atoms directly, exciting them, cooling them, then re-exciting them again in perfect time. NASA's Goddard Space Flight Center reanalyzed older data from when the comet had passed near Mars. The nickel peaks were present there too, only weaker. The fact that they intensified after perihelion suggested that the process wasn't passive. It was evolving. As the comet absorbed sunlight and charged particles from the solar wind, its nickel emissions became more coherent, more refined, as if the energy was being directed. Some within ESA began to speculate that the metal wasn't distributed randomly inside the nucleus at all. Instead, it might be concentrated in an internal lattice, a structured framework acting like a conductor or resonator. In that model, the nickel could function as a natural amplifier for electromagnetic energy. Under the influence of sunlight or internal charge, it would radiate sharply, then relax, producing exactly the kind of periodic signal observed. This theory bordered on forbidden territory, implying order where there should be chaos. But the numbers forced the discussion. The nickel bands were too narrow, too pure, and too synchronized to result from thermal variation alone. When ESA finally released its sanitized summary, the phrase used was anomalous nickel enrichment, potentially due to selective sublimation. Yet internally, the notes told a different story. One draft, later leaked to the scientific community, ended with a single line underlined in red. No natural process can isolate nickel to this degree under current models. It meant what many already feared. 3I Atlas wasn't behaving like an inert relic of another solar system. It was refining itself, sorting, energizing, and perhaps even using its metallic core as part of a larger function. From that moment on, the nickel signature ceased being a curiosity. It became a fingerprint of intent, a repeating proof that somewhere inside this cold interstellar traveler, metal was remembering its purpose, and the universe was watching a machine pretend to be a rock. When 3I Atlas first entered our solar system, its velocity alone made one thing certain: it could never be captured. Like the interstellar traveler Oumuamua before it, 3I Atlas was moving too fast, on a hyperbolic path that guaranteed escape. But after perihelion, the data began to whisper something extraordinary. Its outbound trajectory wasn't quite what physics demanded. The comet wasn't leaving at the speed it arrived. It was slowing ever so slightly, but undeniably, as if something had taken hold of it. At first, astronomers blamed the usual culprit, outgassing. As comets heat up, jets of sublimating ice can act like miniature thrusters, altering motion by a few meters per second. But the numbers didn't fit. Using telemetry from the European Space Operations Centre, analysts compared inbound and outbound velocity vectors. The difference wasn't a few meters, it was nearly 12 kilometers per second of unexplained deceleration. That's orders of magnitude beyond what gas vents can produce, and the effect was perfectly symmetrical across each observational window. The term capture trajectory first appeared in an internal NASA-ESA joint note titled Post-Perihelion Deviations in 3I Atlas Orbital Parameters. The document's authors used careful language, non-gravitational perturbation, consistent with temporary solar capture. But buried deeper in the appendices, a more daring sentence appeared. Object exhibits signs of velocity matching within a planetary frame. In plain terms, 3I Atlas was aligning itself with the orbital speed of Mars. Goldstone radar data confirmed the trend. During the comet's closest approach to the Martian orbital path, Doppler measurements showed a reduction in outbound velocity that couldn't be accounted for by solar drag. Instead, the deceleration followed, a curve smooth, deliberate, mathematically elegant. It wasn't a stumble through space. It was a controlled glide. The object's course was bending, slightly but unmistakably, toward the ecliptic plane, the same flat sheet where all planets orbit the Sunday. For days, analysts thought it must be an illusion caused by parallax, but independent observatories on Earth from Chile to South Africa confirmed identical positional shifts. 3I Atlas wasn't following a true escape trajectory anymore. It was flattening its angle of exit, trading hyperbola for ellipse, as if something had modified its orbit mid-flight. ESA simulation teams tried to model the change using every known variable: solar radiation pressure, gravitational resonance, even interactions with Mars's thin atmosphere. Nothing could reproduce the deceleration profile. The only model that worked assumed the object had actively reduced its own velocity, a scenario that, on paper, required an energy release equivalent to several nuclear detonations spaced across its surface. Yet no explosion, plume, or flare was ever detected. The deceleration happened silently. One theory emerged controversial, whispered only in private calls between agencies. It suggested that 3I Atlas might not have slowed down through thrust, but through field interaction. If the object possessed a magnetic or plasma envelope capable of coupling with the solar wind, it could, in principle, create drag without mass ejection. That would explain the smooth, continuous slowdown and its synchronization with solar flux variations. Essentially, it could be using the sun's own field as a brake. By mid-December, orbital simulations revealed another shock. Extrapolating its course forward, 3I Atlas was no longer destined to vanish into interstellar space. Instead, its new path showed a long, looping arc that would bring it back toward the inner solar system, crossing the orbit of Mars again in late 2031. The numbers hinted at partial capture, as if the object had settled into a vast, weakly bound solar orbit. NASA's Jet Propulsion Laboratory quietly confirmed the same thing. In an internal bulletin, the agency labeled the case as anomalous retention event. To the public, however, both agencies stayed vague. ESA's press statement framed it as orbital uncertainty due to dust ejection, but within the scientific community, that phrase became a euphemism. Everyone knew dust was cover for something else. If the trajectory truly represented capture, it would mean an interstellar object had just performed the rarest maneuver in astronomy, slowing down enough to stay. No natural body could do that. Gravity doesn't bend that way without intervention. And so, the word capture gained a new weight. It no longer referred to the sun seizing a stray object. It hinted that 3I Atlas had captured itself, tuning its motion, matching its velocity, and choosing to remain. In orbital mechanics, there's no such thing as coincidence at this scale. There are only equations, and something inside 3I Atlas seemed to be solving them, not reacting to gravity, but cooperating with it. The sky, once thought to be watching a comet depart, was instead witnessing a decision, an object that came from the stars, finding reason to stay within ours. By January, 3I Atlas had slipped beyond the reach of public observation. Its once luminous coma dimmed, its plasma tail fragmented, and the comet that had unsettled astronomers for months seemed to vanish into the dark. For casual observers, that disappearance marked the end of the story. For the scientists who had been tracking every frequency and photon, it marked the beginning of something stranger, because the silence that followed wasn't empty. It was structured. It started with the absence of noise. When the ESA's deep space antenna at Cerberus re-aimed its dish toward the coordinates of 3I Atlas's last known position, the spectrograph didn't show random static. Instead, it showed periodic gaps, blank bands in the radio spectrum spaced with unnerving precision. They repeated every 9.8 hours, the same interval that had defined the comet's light, magnetic, and thermal cycles. The object might have faded from sight, but its rhythm was still echoing, like the afterimage of a pulse lingering in deep space. Engineers thought it might be internal interference, a harmonics artifact from the dish itself, but when they checked the secondary antenna in New Norcia, 1,400 kilometers away, the same gaps appeared. The pattern was real, external, and consistent. Someone described it as the sound of missing sound. Meanwhile, Maven's magnetometer, still orbiting Mars, continued to register faint oscillations that shouldn't have existed once 3I Atlas had departed the region. The amplitude was weak, less than a nanotesla, yet the timing never drifted. Every 9.8 hours, the pulse returned. Even as the comet moved tens of millions of kilometers away, Mars was still listening, responding to a signal that no longer arrived from any detectable source. In astrophysical terms, it was impossible. Magnetic resonance decays with distance squared. It doesn't persist across astronomical units. The only way for the signal to remain synchronized would be if something either within Mars's atmosphere or in the interplanetary field was sustaining it. The planet had become, somehow, a resonant body. Data from the Solar and Heliospheric Observatory added another layer. Instruments monitoring solar wind detected a faint but measurable drop in background plasma density every time the 9.8-hour cycle peaked. The dips were tiny but perfectly periodic, as though the solar wind itself were being modulated. In total, 4 separate observatories on Earth, at Mars, and in heliocentric orbit, were now detecting the same invisible heartbeat. When the European Space Operations Centre compiled the findings, the report's language grew noticeably cautious. Persistent modulation observed across multiband instruments, no natural source correlation, pattern consistent with coherent external driver. In other words, something is still transmitting, and yet there was nothing left to see. No comet, no glow, no tail, only silence, punctuated by rhythm. To some scientists, it felt as though 3 I-Atlas hadn't left at all. It had shifted mode. What once expressed itself in light now expressed itself in absence. The phenomenon came to be called the residual. The working theory proposed that 3I Atlas had left a trace, a standing wave pattern imprinted in the heliospheric medium. Like the ripples left after a boat passes, it continued oscillating long after the source was gone. But the precision of the cycle, the way it maintained perfect timing across millions of kilometers, defied that metaphor. It wasn't fading. It was alive. In one internal email chain, a researcher wrote, "We used to call this silence. Now I think it's instruction." The phrase spread quietly among teams, half in jest, half in awe, because when they plotted the intervals of the gaps, the missing radio bands, they realized they weren't random at all. The timing formed a binary rhythm, alternating in ratios that approximated prime number sequences. It was simple, elegant, deliberate. Publicly, none of this was acknowledged. ESA's final communiqué referred to the 3I Atlas data stream as signal decay, consistent with diminishing ionized debris. But privately, analysts kept watching the silence. The 9.8-hour rhythm still pulsed, detectable only to the most sensitive instruments, growing fainter but never chaotic. Months later, one last note appeared in the agency's classified summary. Signal amplitude decreasing, coherence unchanged, transmission origin indeterminate, status continuing. For the first time, scientists began to consider that maybe the object hadn't vanished at all. Maybe it had completed its purpose, embedding its frequency into the space it once occupied, turning emptiness into information. And so, as 3I Atlas receded into the cold, the cosmos answered not with brightness, but with pattern. The comet that had once spoken in light now whispered in silence. And that silence, measured and rhythmic, became the final message. It wasn't just gone. It had gone quiet. And in that quiet, it was still speaking.